Okay. Hey, I am Johannes. I am here from MBI. I'm just about to finish my master's, and I've been working on predicting, looking for ultra high energy neutrino signals, for predicting, not really looking for them, from heavy dark matter that's trapped inside the Earth. So, what's the motivation for this? Well, we have, as we've heard earlier this week, there's in the lambda CDM model about 85% of the matter in the density of the universe is dark matter. Sorry, I can try and speak louder. Sorry. Yes. About 85% of the matter density of the universe is, so far as we know, accounted for dark matter, which we haven't found. Searches have traditionally been at the GeV scale for WIMPs and other stuff, and we've begun expanding because we haven't found anything. So what I'm looking for is the ultra high energy neutrinos, and specifically at a scale of above 10 PeV, and because we can possibly use them to detect dark matter through indirect detection. So how are we going to do that? There's a couple of different ways to do dark matter detection. We can do direct detection if we somehow observe a dark matter particle interacting with a standard metal particle. In collider experiments, we can try and hit two standard metal particles together and see if we can I pressed the button, sorry. Lose energy somewhere. We can't find the products, and that's an indication for dark matter. Or we can do it through indirect detection, where dark matter either self-annihilates by colliding with dark matter and producing standard metal particles, or it could also decay, where we only have one dark matter particle, which then decays to standard metal particles. So to do this, we want obviously a higher density of dark matter, and dark matter is distributed across the Milky Way in a halo. There's a few different profiles for this, but as the Earth travels through the Milky Way, it moves through this dark matter halo, where if dark matter interacts with the constituent particles of the Earth, such as the nucleus is making up the elements inside the Earth, the dark matter could lose energy and thus be gravitationally trapped inside the Earth. It will then slowly scatter and lose more and more energy and slowly accumulate near the center. This, of course, would also happen in other celestial bodies, but I'm specifically looking for the case of the Earth if this happens. And we also, I think it was yesterday, we heard about it could also scatter off electrons. My work has been focused on the nucleus. The capture rate of dark matter inside the Earth is given by, the change in dark matter particles is what we call the capture rate. We can calculate it through a long expression that's based on the local dark matter density, which we take to be, in this plot at least, take to be 0.3 GeV per cubic centimeter. The velocity distribution of the dark matter, which is, we take it 270 kilometers per second. And we can see that it produces capture rates, and we can then calculate them individually for each element inside the Earth, because it will have dark matter will have a different cross section with each element, which is accounted for in cross section dark matter for element I. And we can sum all of those and how much they make up of the Earth and find out the capture rate. And we can see this produces at the lower GeV scale certain features, which are resonances when the dark matter mass approaches that of the nuclei making up the Earth. And the highest peak is that of iron, because it makes up a lot of the Earth. I have plotted here for two different cross sections for the dark matter nucleon cross section. We can see, but at the higher energies that I'm working at, the resonances really doesn't matter at all. We have very low capture rates because there's less dark matter particles, and so they interact less, and we capture less dark matter. Obviously, if dark matter decays or annihilates, we don't just have the capture rate, and the change would also be there would also be a component where dark matter either decays or annihilates, depending on the case. Decay scales linearly with the number of particles, where annihilation scales with the square of the number of trapped dark matter particles, because you need more particles, we get trapped closer, there's a higher likelihood of decay. No, annihilation, sorry. There's also something called evaporation rate. It could theoretically escape dark matter. Once it's inside, it could be upscattered in energy, but for very heavy dark matter, as I'm working with, the evaporation rate is effectively null. So we can leave that out for now. This also shows that at some point, the capture rate will be equal to the annihilation rate or the decay rate, and we will reach equilibrium. We have this equilibrium time scale tau, which defines when equilibrium is reached. And for decay, for annihilation, it's based on this 1 over the square root of the capture rate and an annihilation constant, Cn, which is not, I haven't included here, it's details. But at the equilibrium time point, we would obviously have that they're equal, and because for annihilation, we obviously lose 2 particles every time we annihilate, it would be half the capture rate, the annihilation rate at equilibrium. But the Earth is probably not at equilibrium. It depends a bit on which numbers you plug in, but with the numbers that make sense, the Earth is not considered to actually be at equilibrium. The Sun is probably at equilibrium, if we even have dark matter capture. So as dark matter is trapped, as I said, it accumulates near the center of the body, and it makes a distribution around the core. And this plot shows what I call the significant radius, and like how the accumulation of dark matter particles and the radius of Earth. And we can see for the ultra heavy, super heavy dark matter particles, we are effectively within 5-10 kilometers of the Earth's core, everything is. So we can effectively treat them as a point source located at the center of the Earth. This is not the case for lighter dark matter. And these curves aren't correct either, because we assume a constant temperature. There wouldn't be a constant temperature when we go to like 1,000 kilometers away from the core. So how do we get neutrinos from dark matter? Well, you can decay or annihilate, as I've said before. We can, in my study, we assume an equal branching ratio for each neutrino species to 1/3 of each. But there's also other processes which could create neutrinos if dark matter annihilates or decays to other standard matter particles, which when decay. But I've focused on these because they have this channel, because it has the best prospect, because it produces the highest neutrino flux. So what is the neutrino flux from dark matter decay? There's some, I don't remember his name right now, but it's been computed. There's several different things, but I'm using data from H spectra, which has dark matter decay and neutrinos. And we can see here the flux this is from 1 decay, 10 to the 8th GeV, dark matter particle, which would be, and then we need to scale that by the number of decays to get the actual flux, but that's not what I have here. And that's produced inside the Earth are the solid lines for all neutrino flux and for the different flavors. And we have a peak, which is close to half the dark matter mass. And then electric corrections means we also get this trail of lower energy neutrinos when we include them. Then as we propagate, because we have ultra high energy neutrinos, we can actually interact with the particles inside the Earth, which means our flux is attenuated. And we can see this is propagated from the center of the Earth to the surface. The dashed lines, we can see how we lose some of the flux during this propagation. Tau neutrinos could undergo what is called tau regeneration, because the tau's lifetime is on the scale where it decays before it loses any significant amount of energy. And we can actually also see this at the lower ends of the tau spectrum, where we have a higher flux at the surface than we have produced at the core when dark matter decays. Because instead of attenuating the flux and losing neutrinos, we just shift them to lower energies. So we have a lot of background fluxes for this, which are what usually we would look for when we look for ultra high energy neutrinos, what comes a background, this cosmogenic neutrinos and astrophysical neutrinos in this energy regime. We're not interested in seeing those. We can divide our backgrounds into 3 different parts because we would also have backgrounds coming from dark matter decay or annihilations happening elsewhere, because it wouldn't just happen inside the Earth if it's happening. So we can here plot, this is for the NFW profile of the dark matter galactic halo. I won't go into too many details about that. It is a bit hard to see here on the plot. It's better for the Burkhardt profile, but I've included this. You can see the Milky Way center would give us the highest signal because the density is higher there of dark matter. But there is, I don't know if you can see it. If you get close, you can see that there is a significant difference right here at directly upgoing when we include the dark matter trapped inside the Earth. So how are we detecting this? This is geared towards the radio detection at IceCube Gen 2 detector, which aims to install a radio array for detection of radio waves produced by the Ascarian effect, which is when a particle moves through a dense dielectric, at speeds higher than the phase speed of light. It produces radiation and loses energy, which the radio array at IceCube Gen 2 should be able to detect. And yes, that's how we are going to detect it. We have some predicted event rates, which is for my sample case, and currently I need to computing a larger case with more different values. Different more values of the dark matter mass and lifetimes and such. And it is not very high, for this is for 10 years of exposure, but it is significantly higher from the predicted astrophysical background, which is scaled to the current maximum allowed from signals. And yes, and this is for directly upgoing neutrinos only. And yeah, I'm currently working on producing limits when they need to compute more, and the event rates are low, but they're higher than expected.
Thank you, Johannes. Is there a quick question because we are running out of time? Yep.
Maybe it's actually not a question, but a comment. So you show the distribution of the dark matter inside the Earth, right? And you use the function from a paper by Aaron Vincent, if I remember correctly. But this is an outdated distribution, the up-to-date distribution that actually will shift the heavier dark matter concentrate more to the Earth. So you have more dark matter near to the core of the Earth instead of distribute close to the like 1,000 kilometers over there. So
that's for very light dark matter.
Yes, no, but then it actually will shift it go to the core more. But we can talk later. So yeah.
Okay, yeah. The light dark matter was mostly an illustration because I'm not actually working with that. I'm only working with the.
Huh?
I'm only working with the higher than heavier dark matter.
Yeah.
Which are at the core. Yes, thank you.
Okay. Let's thank Johannes again.